Previously, we showed how Fluence response curves are built from experimental data. How do we compare the effects of the different wavelengths of light on the biological response? First off, we need to consider the purpose of our pupil constriction studies and Fluence response curves. By testing the effects of different wavelengths of light at varying intensities, we are testing the sensitivity of the eye to these different wavelengths of light. As we talked about earlier, the shapes of the Fluence response curves are identical between the different wavelengths. The only difference is where it has shifted on the x-axis on the scale of intensity.
We'll begin by taking a single point off of the Fluence response curve that represents the overall pattern of the curve. Importantly, we want this point to represent the shift on the x-axis. A common point used for this kind of curve is called a half maximal response point, or an inflection point. An inflection point is the point on the curve where the response generated is half of the maximum level of response. In our case, this inflection point will be the 50% pupil constriction mark. On the curve, you'll see that this is also where the slope tends to be steepest, around this section. We can find the inflection point for each of these curves by seeing where they fall along this dotted line. For 500 nanometers, we can see that the inflection point for the curve is around 10 log photon flux. For 450 nanometer light, we can see that the inflection point is around 10.1 log photon flux. For 400 nanometer light, we can see that the inflection point is around 10.35 log photon flux. And finally, for 600 nanometer light, we can see that the inflection point is around 10.5 log photon flux. The important thing about inflection points is that they represent each of the Fluence response curves. They also represent the sensitivity of the eye to the different wavelengths. Based on this, we can rank the different wavelengths by the effect that they each have on the eye and on pupil constriction. If we look at the 500 nanometer light Fluence response curve, we can see that it is shifted most to the left relative to the other curves. This indicates that the eye is most sensitive to 500 nanometer light, and that it requires the least amount of light of this wavelength to reach 50% pupil constriction. If we look at the 600 nanometer light Fluence response curve, we can see that it is shifted most to the right of the graph. This indicates that the eye is least sensitive to 600 nanometer light, and that it requires the most amount of light of this wavelength to reach 50% pupil constriction.
So how do we plot our findings on a graph? Sensitivity is an abstract measurement, so in order to compare the effects of our various wavelengths on pupil constriction, we will use relative sensitivity. To do this, the wavelength of light that the eye is most sensitive to will be used as our maximum sensitivity reference. Other wavelengths will be expressed relative to the reference. The wavelength with the highest sensitivity will be defined as having a relative sensitivity of 1. By quantifying the effects of all other wavelengths on the eye relative to the maximum sensitivity reference, we will be taking into account how much more photon flux is needed of a wavelength of light to generate the same level of response as the wavelength the eye is most sensitive to. Remember that needing more photons means the eye is less sensitive. If we know the amount of light needed to get the same response for both the reference wavelength and any other wavelength, the relative sensitivity for the tested wavelength can be calculated by taking the ratio between those intensity values. That means that a wavelength that needs 2 times as much light as the wavelength the eye is most sensitive to will have a relative sensitivity score of 0.5, which is calculated by dividing 1 by 2. So how do we plot these relative sensitivity values on a graph?
We'll be plotting our inflection points on a graph with an x-axis of wavelength in nanometers, and a y-axis of relative sensitivity. It's important to note that relative sensitivity does not have any units and that it ranges from 0 to 1. We'll begin by plotting our maximum sensitivity reference point that has a wavelength of 500 nanometers here and a sensitivity that is designated 1. So we'll plot that here. Now let's look at the Fluence response curve for 450 nanometer light and compare it to the curve for 500 nanometer light. We can see that relative to the 500 nanometer light curve, the 450 nanometer light curve is shifted more to the right, which indicates that the eye is less sensitive to 450 nanometer light. In this case, we needed 1.2 more times of photon flux than 500 nanometer light. So we can say that the eye has a relative sensitivity of 0.85 to 450 nanometer light. This was calculated by dividing 1 by 1.2. So we can plot this on the graph relative to its wavelength, which is 450, and to its sensitivity, which was 0.85, which will be around here. We can do this as well for 400 nanometer light. In this case, we needed 2.2 times more photon flux of 400 nanometer light than 500 nanometer light to reach the same level of pupil constriction. So we can say that the eye has a relative sensitivity of 0.45 to 400 nanometer light. And we can plot that on the graph here. And finally, for 600 nanometer light, we needed 3.3 times more photon flux of that wavelength than 500 nanometer light to reach that 50% pupil constriction mark. So we can say that the eye has a relative sensitivity of 0.3 to 600 nanometer light. And we can plot that on the graph here. Remember that in most experiments of this kind, they would use more than just 4 wavelengths. However, for the purposes of this tutorial, we will just stick with these 4. So if we draw a curve through these points, like so, we get a graph that is called an action spectrum. An action spectrum is a graph that represents sensitivity on the y-axis as a result of changing the wavelength on the x-axis. We've used Fluence response data to normalize the interaction between these two factors. This kind of graph also helps us to visualize any patterns in the raw data that we may have missed.
From this action spectrum, we can see that the eye is most sensitive to 500 nanometer light, which is commonly perceived as green light. This point is indicated by the peak in the curve at 500 nanometers. This isn't a surprise. You can see that we've already used this peak point as the basis of the curve. So what are the benefits of presenting our data in an action spectrum rather than a set of Fluence response curves? Similar to how Fluence response curves simplified and cleaned up the experimental results, an action spectrum condenses the information from Fluence response curves of many wavelengths. This graph allows the researcher to make a clear association between a change in wavelength and the response being measured. Again, having all the relevant information in one graph allows a pattern to be recognized easily. Considering how much data went into generating this curve, it is not surprising that action spectra are difficult to interpret. Now that you know that an action spectrum is a replotting of key features from many Fluence response curves, you should be able to mentally work backwards to see where the curve came from. The data on light sensitivity are very informative because different types of photoreceptors have different characteristic action spectra. Often, scientists can guess at the type of photoreceptor that is involved in a certain response by experimentally generating an action spectrum and looking at its shape. A good example of this property is the recent discovery of mammalian melanopsin, which is a photopigment involved in non-image forming systems. Based on the action spectrum for pupil constriction and other non-image forming photic responses, scientists had already predicted that the photoreceptor was likely an opsin, even before it was fully characterized in the mammalian retina. In this series of video tutorials, we learned about how to conduct pupil constriction experiments and create and interpret Fluence response curves and action spectra. Check out the BioClock Studio's channel on YouTube if you're interested in more videos made by the BioClock Studio.